and then we'll see when we end. Welcome to a talk that we submitted with this title because Chuki said she didn't like the title I used for some other conference last year, which was something something Android something something. So this today is going to be something in particular about Android, and then they got picky and tried to nail me down on an actual topic a couple of weeks ago when they were panicking about this. So we decided we would talk about performance instead. So this is going to be about finding and fixing performance problems, or at least that was the theory. We thought we'll do a use case and case study and use all these tools and find the problems and then fix them and show you how that works. We didn't quite get all the way there, so it's really more about finding the problems. So we're going to walk through a lot of the tools that we use on pretty much a daily basis when there are performance problems and analyze what's going on and sort of show you how that works from the inside. I guess we should actually say who we are. I'm Chet Haase. I'm on the Android UI Toolkit team. All the widgets on the screen and the graphics stack to display that.
And I'm Romain. I'm on the Android graphics team.
And we have dealt with these kind of performance problems a lot over the years, so we'll sort of show you how that works. So we can also call those fantastic tools and where to use them. So let's go. So some of the tools, I saw Andrea did a talk yesterday about some of the developer options. So we're going to cover a little bit of those, a couple of those tools in a little bit more detail, but then a lot of other more host-side tools as well. So we thought, well, instead of writing a demo app and sort of coming up with this fake problem, it'd kind of be nice to use a real app. A few years ago, maybe 3 or 4 years ago.
Yes, I wrote a long explanation of our developer tools. It was an analysis of an application, a Twitter client called Falcon Pro. And if you haven't read the article, I don't remember what it's called, but if you look up my name and Falcon Pro, you'll find that long article. It's a more detailed version of what we're going to talk about here. And yeah, we like the idea of taking an existing application and showing the kind of real-world performance issues that you might encounter. So we went on the Play Store. We started looking at a lot of apps.
So we thought, okay, well, we'll start there. We'll look at Play Store and see what we can find. And what we found was there's an app on the Play Store called Play Store, which seemed to demonstrate kind of the jank that we were looking for. So let's go ahead and play this again. And what we're looking at, so we're going to scroll down on the main page and then back up, and then we're going to go into a detail view, scroll down and up, and then back to the main page and down and up. And what you're looking for is the times in an application's life where you're not running at 60 frames a second, where basically there's a pause, a noticeable pause while it skips at least one frame, often more.
Well, in the case of the Play Store, we were really looking at when it's running at 60 frames per second. It's not often.
Yeah.
So as you can see, every time we start to scroll, it's a little hard to see on the video, but there's a huge jank. Like the UI thread is blocked for up to like 300 milliseconds. And it's every time you go to a new screen. So if you're on the home page, you scroll, it janks. You go to a detail page, you scroll, it janks. You go back to the home page, you scroll, it janks. Yeah, it's not doing any caching, but we'll see that's not true. It's doing a lot of caching. So I don't know why, because it's not helping.
And it is, to be fair, it's a really complicated app. There is a ton of media coming in, a lot of information. They're pinging the server on, they're downloading bitmaps, they're doing all kinds of stuff to get the information they need to display, and they're doing some nice stuff, like they have some placeholder images so that you see this little gray rectangle, so they're not like janking as they load every single bitmap, but clearly there's a lot going on there, but maybe some of it they could actually, this random app, I don't know whose it is, could actually take a look at some performance and maybe fix that. So what will we do to analyze that? Well, first of all, we'd figure out how to use slides. There we go. Okay, so one of the areas we look at is Overdraw. I'm not sure if this was shown yesterday in Andrea's talk or not, but
I'm sure it was.
Okay, it was. Sure, it was. So go into developer options, and you can click on this nice little dialog here, and it says debug GPU overdraw. Show the overdraw areas, and that's going to paint the screen in lots of pretty colors. It's going to look like that.
Yeah, so the color scheme, you can blame me. I picked all those colors. I did my best. So the colors have different meanings. So the concept of overdraw, we talk about overdraw when you draw a pixel on top of another pixel that we've already drawn. So when you don't see any color, that means you've drawn the screen only once. When it becomes blue, we have an overdraw of 1x, which means we've drawn that pixel twice.
It's a zero-based array. Right?
Yeah, it's an off by one error.
Yeah.
When you have a 2x overdraw, it's green. Then light red means 3x overdraw. And then dark red is 4x overdraw or more. And we stopped there because I ran out of colors that worked, honestly. It's really hard to find colors that work in most applications, trust me.
If only you knew more about color.
Yes, if only.
Okay.
Anyway, so overdraw is very important because for many reasons. One of them is usually when you have a lot of overdraw, it means your hierarchy of views is probably more complicated than it needs to be. It means you're doing more inflations, using more memory, we're doing more traversals in the framework, so everything gets a little bit slower. So that alone is a good reason to optimize everything. And then the problem is when we draw pixels on top of each other, when we have to do blending, so when there's transparency involved, which is the case of almost everything that you see on screen, what happens is that the GPU has to read back the pixel that's already on screen. It has to read the new pixel you want to write from memory. Then it has to blend them together and write the output. So it's very costly in terms of computations, but also bandwidth. One thing to remember is that the number of cores have gone up over the past few years. The speed of each core has gone up. The instruction sets of the CPUs have gotten a lot better. Some of the instructions are actually extremely ridiculous. They can do many things at once. The GPUs have gotten a lot better. We can run many more instructions than we could just a few years ago. What hasn't changed at all since about 2011 is the amount of bandwidth that you have in the phone. So it's about 20 to 30 gigabytes per second. And to give you an idea, desktop today, like the GPUs today we have on desktops, they are several hundreds of gigabytes per second. So we have, we are an order of magnitude or two behind desktop, and it's completely flat. It's not going up. I hope it's going to go up. But the problem is when you have overdraw, you're wasting that bandwidth, and we're going to run out. And we have more and more pixels on screen. Our displays now, they are 1080p or they're 2K. There are 4K phones out there. I wouldn't be surprised if there are 8K phones that are coming or that exist already. So we're adding more pixels, but we're not adding more bandwidth to draw those pixels. So you have to be extremely careful with overdraw.
So some overdraw is to be expected. So an easy case, so you see like there's a light red on the search bar up at the top, and then there's dark red for the text. Well, it's not like you're going to draw the text without drawing the background underneath it, right? So you're going to overdraw some areas. That's totally understandable. What we're looking for is problematic areas where we're overdrawing where you really shouldn't be. So there's a couple of interesting things here. Actually, before we get back to the play thing, we noticed when we were analyzing this yesterday, look up at the top, the status bar up at the top with the icons, like that's already red. Like the background of the status bar, something's going on there. Some of the icons are different. You can see this. Most of the icons are blue, so there's a 1x overdraw. That's fine. You're drawing an icon over a background. That's cool. But the battery, that's probably because, so compare Wi-Fi and battery, right? Wi-Fi does not have extra overdraw, probably because they have individual icons that represent the different states that can be in, right? So when they draw the state of Wi-Fi, it is just a thing. When they draw battery, my understanding of looking at this is they're drawing the outline of a battery and then they're filling it in according to some measure of what that is. So instead of having 100 different states of the battery icon, they just have one represented by the actual floating point state of what that charge is or whatever. But that means another overdraw. Fine, not a problem, but it's just sort of interesting to see where these things are at. I'm not sure what's going on with the red background there. The one I like is the home button down at the bottom.
It's a mystery. We don't understand why.
I mean, maybe I pressed that button when I took this screenshot. I don't think so. So why are the ones on the side blue? Blue is fine. They're drawing a background. They're drawing an icon. Blue is to be expected. But red for the home? I don't know what's going on.
Home is an important button. Maybe they draw it several times to make sure it's there on screen.
So the one that we were curious, though, about the actual Play Store app was the blue in the background. This is kind of an indicator. So this is basically like everything there starts with a 1x overdraw, right? And this typically happens when you're drawing a window background, which is cool. If you don't draw a window background, you can get some artifacts. It's kind of a good thing to avoid. It was a nice hack back in the day, but really don't do that anymore. But if you have that background, you're apparently drawing on top of it as well. So we were sort of curious where that came from. So we used Hierarchy Viewer to take a look at that. Hierarchy Viewer is awesome for looking at stuff. There is a replacement for this in Android Studio. It doesn't have all of the same functionality, but that's coming online more over time, and it'll probably be better and easier to use.
It's called Layout Inspector.
Long run. So you have the views represented by the tree on the left. You have this thing up in the right, which is like all the views, and then you have this blueprint diagram of the layout of all the views in the lower right. And then you can click on the views and see more information about it. So if we deep dive here, we can see that we're drawing a white background, basically the size of the screen, the size of the window, right? So we have a window background, and then they really wanted to make sure that it was white, so they created their own background to draw right on top of that, which means we're drawing it for the window, and we're also drawing it on top of that. So you never see the window's background, you only see this. The other interesting thing I noticed here is, okay, totally reasonable, there's a frame layout with a background. But actually, this is a frame layout with no children. It is here only to hold the background. It is a child of a frame layout. That parent frame layout could have drawn the background. I'm not sure why they have a child in there to have the background. Maybe there's good logic for this, maybe there's other states that I don't understand, but we're just sort of poking at this from the outside, sort
Separation
of
of concerns.
seeing what's going on. Yes, and I have concerns. Okay, so the other thing we noticed when we pulled up hierarchy viewer.
Yeah, so Play Store has a few views in its hierarchy. I mean, the Overdraw was an indication of that, but we were a little surprised when we saw the actual hierarchy. So that's the tree of views. If you can't see anything, that's completely normal. Actually, so hierarchy viewer has this option where you can export the tree of views as a PNG. And I wrote that originally to shame. The first time I did that, I actually printed it on, I think it was like 30 sheets of paper. There was Gmail back then. And I taped it on the walls in the office to just shame them. Anyway, so the problem here is that hierarchy viewer could not export that file because it was running out of memory. So I had to hack hierarchy viewer to request 4 gigabytes of heap on the desktop to be able to export the PNG. Now, we got the PNG, and Apple Preview could not render it. Google Slides would not let us upload it because it was too large. So we had to use Photoshop to downsample it. And here is what it looks like. So if we start at the top, so that's been resized to fit the screen, you know, the width of the screen. So here's the full hierarchy of views. You know, there's a few. And the problem is, you know, it's not only about performance, but it's also for you, where's slides? It's also for you because it probably is extremely difficult to maintain and debug. Like when you have that many views, no matter how good you are, there is no way. How much time did it take you to find that view in that whole mess of?
Yeah, dragging around here, like following the lines up vertically. Yeah, not easy. Yep.
So do yourself a favor, like have fewer views.
So we thought, well, how many views
are
actually in the app?
Yeah, so, yeah.
So there's a couple of different ways to find that out. One is there's a lot of different information you can get from a command line tool called gfxinfo. So you can just call it without an argument there, without the package argument, and it'll give you information on everything going on in the system. Or you can give it the package argument, it'll give you information that's specific to that application. So we said, okay, gfxinfo on the Play Store app, and it gave us all this stuff. So just to give you a broad overview of some of the information you'll see in there, this is what we call jank stats or frame stats. I'm going to talk about that a little bit later when we talk about FrameMetrics APIs. It's basically the information on what is your what's going on with your rendering. How long are you taking to render your frames, and how often do you go above the line that you don't want to go above? Like how often are you janking because you're not running at 60 frames per second? So this is sort of good information to keep an eye on. Next we have a bunch of memory information.
Yeah, so the memory information, if we can zoom in on it a little bit so you can read it. I hope that's better. So those are caches. This is the state of caches that are internal to the rendering pipeline. Slide. And most of the time, you don't need to worry about those, but it's a good idea to look at them from time to time, because if those caches are saturated, if you see that some of them are full most of the time, that means you're thrashing the caches. And what it means for the rendering pipeline is every time you thrash the cache, we have to do a lot of management. We have to go find, you know, items that we need to delete to be able to insert the new items that you want to draw on screen. So it can be particularly useful. The ones that are interesting to you, the font renderer, you don't have to worry about it too much unless you're using tons of emojis. The ones that matter the most are the path cache. So that's used for drawing anything that's vector-based. So if you use a lot of animated vector drawables, and you have large vector drawables, or if you use a library like Lottie that uses a lot of vectors, you might want to take a look at this. The text drop shadow cache is also interesting. If you use, if you set a shadow layer on a text view or if you use Paint and you set a shadow layer on your Paint to draw text, those drop shadows are extremely expensive to compute. Because we have to compute them for a single line of text at a time. So it's very specific to that draw text. We can't reuse it for any other piece of text. So you might want to keep an eye on it. And the rest is not that important for your applications.
Texture cache is an indication of how many bitmaps you have active at any point.
Now,
well.
the thing we're interested in is at the very bottom, we give you the total number of viewroot impl. So you might not know what viewroot impl is. It is hell for us. If you're curious, go in the source code of Android, open viewroot-impl.java, look for a method called perform traversals. It's something like several thousand lines long.
No, it got refactored. Now it's like 3 or 4 methods of several hundred lines each.
Oh, my bad.
Yeah, so it's much better.
And it has hundreds of booleans that are more or less equivalent to each other, but not quite. Anyway, that's what drives everything on Android. That's layout, input, animations, drawing. It's one of the most important pieces of the system, and also one of the hardest to maintain and understand, of course. Anyway, so every window on screen has a viewroot impl. So that's basically the number of windows you have on screen. So number of dialogues and activities and anything that creates a window will get one of those. What we care about here is the fact that we have 450 views. So that's the giant diagram you saw earlier, and honestly, you open the Play Store and you look at the screen, and if you were to ask me to use 450 views to recreate the same screen, I would find that difficult because at some point I would just run out of ideas on how to waste views. But apparently they're more creative than I am. And the last line is also interesting because a view is a fairly expensive object on Android. It's not just about computation, but it's about the size in memory. Every view comes with text and drawables and all that stuff. But even if you ignore all the data that's associated with a view, the data structure of a view itself is not that cheap. It's around like half a kilobyte to a couple kilobytes per view, which doesn't sound that much. But then we have hidden structures like display list. That's where we record the canvas commands, and you can see that we have half a megabyte of just drawing commands stored in memory for all those views. And if some of those views are not required, then we're wasting memory.
So these views are obviously not all visible, but they are all attached. So they may be invisible or gone in the tree, but they're in the tree. We saw them in the tree. That's what hierarchy viewer is good at showing you.
We thought that Play Store was bad, but turns out it's actually way worse than we thought. Because yes, there's this other tool called meminfo. So it works the same way as gfxinfo. If you call meminfo without an argument, it's going to print the memory information for every process in the system. If you specify the name of your package, you get a dump that looks like this. We're not going to try to explain like the breakdown of everything that's on screen, but there's a very interesting section here.
Memory details. Go look at that. You can figure it out. PSS, heap size, all that sort of stuff.
All right, so number of objects. So that one is interesting because, we see that now we have 722 views, but gfxinfo says there are only 450, well, only 450. So the difference is that gfxinfo only prints information about what the UI toolkit knows about. So those are the views that are in the window that we're going to process to draw. This number is what the Arch runtime, or Dalvik on older versions of Android, knows about that class. So there's I think it's in Android.os, there's a class somewhere, maybe a runtime or debug, whatever. There's a method in the system that you can call. You can say, tell me how many instances I have of a particular class. So that's what we do here. We just ask the runtime how many instances of views exist in RAM right now. And the answer is 720. That means that the Play Store is caching views somewhere. It's trying to hide them from the UI toolkit, so we don't know about them, but they're there somewhere. And they're taking a huge amount of memory, and given the performance, maybe they're not used in the best way. And this is actually a pretty low number. When we were playing with the Play Store, we saw that number go up to like 4,000 or a couple thousand. Yeah, so that's a big waste.
Zoom out there.
Yeah.
All right. So that was the end of that path. Okay, something is going on with number of views. It'd be nice to check that out. But there are other things that we can use to find out more about performance. We can profile GPU rendering. So again, we go into developer options, and we can say, okay, profile these on screen as bars, and this shows you a pretty output that looks like this. So basically, foreground activity, it's going to be showing all that stuff down at the bottom. And the thing that you want to keep in mind is that horizontal green line. That is a 16 millisecond line, and it's problematic whenever you see the bars, the histogram bars, pop above that. That means that a frame, whatever frame caused that histogram bar, popped above 16 milliseconds, which means that it didn't run at 60 frames per second for that frame. Doing it occasionally, especially when you're popping between activities, expected. Doing it frequently, bad. Doing it constantly, horrible. Right? So it would be nice to see what's going on with the Play Store app. So we can run another video here, and we're going to do the same scrolling and going into the detail activity thing as we did before, and then we'll see what GPU profiling says. It says some incredibly huge spikes, and a lot of spikes that take it just a little bit above, and then in this one, ugh, right? So you would think, well, if it's bringing in content, you know, for that new scrolling area, maybe that's causing some, even when we go back to the activity and it's bringing in some of the same contents, we're still losing a lot there, right? So we're popping up, we're probably missing 2, 3, 4 frames at a time really frequently there, right? So it'd be kind of nice to chase that down, profile that, and see what's going on. So there are different ways to profile, lots of different tools that you can use, and more coming online all the time. Android Studio 3, I think it was in 2.4, early version of this stuff, but certainly in 3, we're using the Canary right now, and we can see profiling tools that they just released, which are pretty awesome. So they're very different profiling tools. They have battery, was that? Oh, it's network down at the bottom, memory, and CPU. So CPU is what we're interested in here, but it's kind of interesting to see some of the other memory stuff going on.
So that's the view when you enable the profiler. So you're going to have a real-time timeline of your application or any other process you can select on the system. And this is the main view that you see. But you can actually dig deeper. By clicking any one of those timelines, you can get more information specific to CPU or memory or network.
So if we take a look at some of the memory information, so we click on that memory and we can see this. So the interesting thing here is this was that whole sequence of like scrolling, going into, going out of, and obviously we're allocating more memory along the way, but it never gets deallocated. So what's going on with that memory, right? So we're obviously allocating memory, sure, we're grabbing bitmaps, you know, we're creating all these things to show you the content to be expected, but if they're going away, why is the heap still this large? That would be kind of nice to know.
Actually, we'll see that it's even worse than it looks.
Okay.
We are deallocating memory, but we're allocating enough that the total doesn't change.
Yeah. We also saw a fair amount of GC or allocation activity. We did like an allocation tracker.
Trace,
Yeah. Okay, so if you select a region in the CPU profiler, you get information that is akin to what you used to get with TraceView, but way better. Right? So TraceView originally was an instrumented profiling tool that would show you the call graph at all times, all of the methods that you're going through so you can figure out where the hotspots are. The problem with TraceView in that original form was that there was so much overhead in instrumenting and running that instrumentation that that would actually skew the results. I myself have optimized code that I shouldn't have wasted time with because TraceView told me it was a problem. The reality was it wasn't a problem at all, but I got skewed results from that. So it's interesting to see what that call graph is, but it's giving you information that may not be relevant. So then they had a sampling profile version of TraceView that would instead just sample it occasionally. It doesn't give you the full call graph history of everything, but it does give you a better idea of hotspots.
Yeah, and so with the new profiler, you can choose between sampling and instrumented. So most of the time you'll want sampling. Instrumentation can be useful if you have a lot of very tiny method calls that might be missed by the sample when we're sampling, and you really want to know how many of those calls you're making. But most of the time, stick with sampling. So once you have this view, what you can do at the top, you can see there's over the CPU timeline, there's a blue area. That's what you can. That's a selection you can just drag and drop to restrict the amount of data you want to see. Just under the timeline, you can see every single thread in the application, and whenever you see one of those green bars, that means that thread is running. So it can be extremely useful too in your application if you have a lot of threads, if you're doing a lot of work in the background, you want to make sure that they're running correctly or they're not running against each other. And finally, at the bottom, there's 4 different tabs. By default, you get this flame chart. So you can read it from the bottom up. this is the root, basically, of the application, and every method call goes up. And it's an easy way for you to see where you're spending most of the time in that selection that we've done at the top. The colors are also interesting. The colors in that flame chart are based, it's a hash of the package names. So all the green bars are application code in this example, and everything that's orange is the framework, it's the platform, it's anything that's Android dot something. So it's an easy way for you to identify quickly whether or not you're either abusing the platform or maybe our code needs optimization or whether your code is at fault. And the other tabs, there's a call chart. That's a different way of reading this flame graph. There's also a top to bottom and bottom up that shows you percentage of execution. That's similar to what Trace used to do.
Even if you're looking at app code, like we're not using some special version, so it's apparently been obfuscated, or maybe they just like really short method names. My favorite one here is c.g.a.f.i.b.
No,
v.f. on layout.
That's the profiler that shortens the package names so that they fit in the.
All right, but the last bit is interesting because, okay, well, maybe one of the expensive things that's going on there is layout code that the app is running.
An important combo box right here. By default, you have the wall clock time. That's how much time the execution took for the user, like the perceived time. You might want to change that to CPU time if you want to not take into account sleeps, for instance. If you really want to know how fast the code executes when it's actually running.
I like that it's still called wall clock time when nobody really uses wall clocks anymore. They should call it pocket time. And then finally, if you're using all these tools and you really want to get all the information you can, you're going to end up in systrace.
Right, so systrace can be intimidating. I know a lot of people like try it once and they see that giant screen full of data and they recoil in fear and they close it and never open it again. It is intimidating, but it's actually a very simple tool. There's not that much you can do in terms of interactions inside systrace. It shows you a lot of data, but as application developers, there's most of it you can completely ignore. So I'm going to show you an example. So we grabbed the systrace of Play Store, that scenario we've kept showing you, and I'm just going to walk you through some of the keys that you can use in the tool to make your life easier, and some of the things that are important for you as app developers. And the rest you can just blissfully ignore. And actually, most of the data in systrace, I don't even know what it is, but I don't care. So this is how you invoke systrace. There's a Python script in the SDK, so you just call systrace.py, and then you can specify a list of tags. If you don't specify anything, which is actually my recommendation, we're going to grab a set of tags that makes sense to inspect your application. Then it's going to wait for your input. You just play with the application. When you're done, you just press enter. It's going to generate an HTML file, and you can just open that file in your browser. The reason why we like to output an HTML file is that it's extremely easy for us to share it. Most of our performance bug reports that we have internally, they contain one of those HTML files. So you can just attach it to a bug, you can send it by email. You don't need a special viewer. The HTML file is the viewer. Where is the trace?
Oh, good question. Desktop. Someone want to sing while I do this? Oh, where is this?
Chet is never prepared. It's embarrassing.
Did I put it here?
I do not know where you put it.
Weird, because problem. Was it your computer?
All right, so this is what it looks like. Like I said, a little intimidating. There's a lot of data there. The parts you care about are the alerts line at the top, and we're going to look at it. There's the kernel section. That section shows all the CPUs in the device and what they're doing at any time. So you can see whether your process is running, another process is running. Actually, you can see what thread is running. You can also expand that section to get a lot more information. And like I said, like all those, for instance, that are called, for instance, DSI, OPLL, Pixel, CLK, SRC. It's a clock, I'm sure, but I have no idea what it is. So completely ignore them. What's interesting when you expand, so at the top for every CPU, you can see what the CPU is doing, but you can see the clock frequency, so you can know whether the CPU is running at full speed or not. And that is important because if you look at the profiler that you get in Android Studio, it's showing you a percentage of utilization. So if your code is using 100% of the CPU, it does matter whether the CPU is running at 300 megahertz or 2 gigahertz, because 100% utilization at 300 megahertz, that's fine. At 2 gigahertz, not so fine.
The other thing about the CPU profiler is I believe it shows you the overall system utilization, which means you may be pegging one CPU out of 4, and it's going to show as low utilization in the CPU monitor. So you kind of want to sanity check that occasionally.
So when you click one of the clock frequency at the bottom here, you can see the value. So wherever I clicked, we were running at 1.3 gigahertz on that particular CPU. So that can be interesting, but most of the time you probably want to keep that section closed. Now if I zoom in on it to see more detail, so if you've ever played a first-person shooter on PC, you know how to use systrace. WASD lets you move around in systrace, and it's like forward, backward, left and right, and you also use the mouse to choose where you're looking. So
don't you love tools written by engineers?
Yeah.
Awesome.
So when I click W, I'm just zooming in, and now we can see what the CPU is doing. We can go here, and for instance, so this thread here was the Play Store, and the other CPUs were doing other things. Go back. Sorry, systrace is difficult to demo on a small screen. Sorry about the zooming in and out all the time. Anyway, so after the kernel section, you have the section for your application. So in this case, we have com.android.vending. That's the Play Store. And there you're going to see a lot of stuff. There's all the threads and a lot of little blocks. What's interesting in systrace, we have two types of timelines. We have counters and we have events. So events are small tags that we put in the code to let us know what the application is doing at a certain time. The counters are exactly what it means. They're just counters. So we can see, for instance, here in the animator section, we can see all the animations that are running. Every one of those blocks is basically, and you can see that the Play Store is running a lot of animations.
Yay.
Fairly frequently. Some of the counters are also interesting if you're into that kind of stuff, but they're not going to be that useful to you as app developers. So for instance, there's a texture counter here. If you go on the left, the HW UI, that's the beautiful name of the UI renderer in the platform. And that just shows us how many textures we have in memory at that point. So you can ignore it, but it can be interesting if you're creating a lot of bitmaps. Anyway, so then you scroll down here, and you have the UI thread and the render thread. So those show you exactly what your application is doing. So the UI thread is where most of your code runs, and the render thread is where we do the rendering. So the render thread appeared in Lollipop. It does not exist on previous versions of Android. Now, so if you want to identify what the Play Store is doing wrong, usually all you want to do is look at that UI thread and identify blocks that look suspicious. So you can see that sometimes we have those extremely irregular patterns. Like here, we have a lot of thin lines. That means we're probably running at 60 frames per second. Everything's going great. And then suddenly, boom, there's this huge block of stuff that the Play Store is doing. So if we zoom in on that, and you can zoom in easily. If you click on event, you can just type F to zoom in on it. So what do we have? We have choreographer do frame. So choreographer is the tool inside the system that tells the UI toolkit to start rendering a frame. When the screen is ready to draw, that thing wakes up and tells the UI toolkit, okay, now it's time to measure and layout and draw. Underneath, we see traversal. So that's what I mentioned earlier in that view-root impl, in that horrible class. That's where we start doing all the work for the UI toolkit. And then we're going into the layout. And you can see here we were probably opening one of the screens. And during layout, for some reason, so that's probably a recycler view or list view of some kind, the Play Store is inflating a lot of views. And if you click one of those events and you go look at the bottom, you can get a lot more information about what's going on. So here we can see that inflating that one list item took 8 milliseconds in wall time and 5 milliseconds in CPU time. That's a lot. So every list item on screen is going to take 5 to 10 milliseconds, and that's how you end up with a layout that took 340 milliseconds. Those are the big janks that you see. And what's extremely interesting too about this is that for every event, when you zoom in, just above the events, you can see those little blocks of colors. They are telling you whether or not the code is actually running. So when it's green, it means that the thread is being scheduled on the CPU, it's being ran. And then we have red, that means you're blocked. There's blue, I don't remember what blue means. And sometimes there's just no color, which means that you're not being scheduled at all. So here, clearly what we're seeing is that the Play Store is doing way too much in terms of inflation. That goes back to them having too many views, and maybe views that are too complicated, or maybe they have custom views that are heavy to inflate. We can find other things. So if we look at the render thread, if we look at what happens when we actually draw something, let me zoom in. So a frame, the part you care about is going to be the beginning of draw frame. There's this section called prepare tree, where we received all the drawing commands, and we do some bookkeeping, we prepare the textures and stuff like that. And in particular here we see uploads. So that's something we have to do when we see a new bitmap or the content of a bitmap has changed, we have to upload it to the GPU. And that's an expensive operation. You can see that the Play Store is doing a few of them that looks fairly big. So when we zoom out, every one of them, so this one is taking 2 milliseconds, this one is taking 1.5 milliseconds, 1 milliseconds. So we have a total of 12 milliseconds just preparing our textures, which is a lot. And the reason is, if I click on one of those uploads again, if you zoom here, you can see the size of the texture. So this one is 1080 by 500. So 1080 is the width of the screen. And for some reason, the Play Store is uploading about half a dozen or like 10 textures that are each really large, but nowhere on screen have we seen those large textures. So I have no idea what they are. And someone who understands the code of their own app should be able to figure that out. But clearly there's a problem. So maybe they're preparing bitmaps for later, but that's blocking the execution of the current frame, or they're just trying to draw bitmaps that are really big, and then they're asking us to scale them down on screen, which is also a bad idea. So yeah, basically that's the kind of stuff you can obtain from systrace. If you scroll at the top, so I mentioned that alerts line. It's very interesting because it has all those little warning icons, and when you click on them, we can give you information about what you might be doing wrong. So the one I just clicked, for instance, is saying that you're doing expensive bitmap uploads. We've uploaded 2.7 million pixels. I'm not sure that that's useful, but you can see that we were uploading a lot of textures. Those are probably fine because they look like icons. There was another one that was interesting, scheduling delay, a long draw.
There's also the tips down on the app.
Yeah, but that's, where's the one I'm looking for? Yes, this one. So this one, if you zoom in on it, it says inefficient view alpha usage. So they have a custom view called doc image view. And what they're doing is they're calling set alpha on it, which is something that you do a lot. Unfortunately, on Android, setting the alpha on the view, sometimes it's super efficient, and sometimes it can be really slow. So the views that are efficient, typically text if you don't have a text view, if you don't have a background, or basically any view that does not have overlapping rendering. So if you don't have a background, you're good. Image view most of the time should be fast. I don't know why this one, doc image view, is slow. We gave a talk, was it a Google I/O? We had a Google I/O talk, I think in 2013 or something. Look it up. I don't remember what it was called or when we gave it, but look it up. We talked about alpha and why we have to do it this way and why it's expensive. But if you see this warning in the alert section, you should take a look at your set alpha calls and see if you can do it better. Maybe you have to use a hardware layer. Maybe you should find a different way of doing it. We don't have time to go into details here. But yeah, look at those little warnings there, because they can give you a lot of interesting information. And usually they have a link to a documentation, to a page on developer.android.com to give you more information about why it's bad and what you can do about it.
There are other tips down in the app area as well, a little more specific to the things that are going on in specific frames, about layout during animation or whatever it is. Yeah. So if it's red, take a look.
Yeah, the little Fs. When it's red, that means we missed a frame, so we're not running like 60 frames per second. And sometimes when you click on it, it can give you more information about what happened.
F doesn't mean funny there. It's usually, the tips are not
failure?
Not funny at all, actually. But No, because F is also in green. Frame.
Yeah,
Frame?
frame.
Frame. I think it means frame and not funny. Okay. That was systrace. Let's see. I want to talk really quickly about frame metrics, mostly so that you understand what they are and you think about how we can track performance in our applications and analyze data maybe offline and maybe more importantly dashboard that data so that you know when you're creating problems in your application for performance. You can think of frame metrics as gfxinfo for your app. So we saw gfxinfo before and the information that it can give you on the command line, and you can get that same information on the app side as well. So we saw it here, you enable that, you see the bars. Well, those bars are actually, well, let's go over this. I wanted to go over this, I don't think we really have time, but the ones that you really care about, that you can do something about are all the green and blue ones there. This is basically stuff that your code could be running and causing problems, like if you're doing layout and layout is taking a long time, you want to deal with that. If you're spending a long time in draw, then you're probably trying to do too much, and we're actually running a lot of code to do that for you on every frame. Input handling, maybe we're just calling you to tell you about that, but maybe you use that as a trigger to go ping some web service. That would be silly. Swap buffers and command issue, you can't affect that directly, but indirectly it tells you how much you're asking the GPU to do on your behalf. Right, so those are the commands we're sending OpenGL commands up there, and then if we're waiting a long time for swap buffer, it means that it's processing commands and it can't get back to you immediately because it's doing a lot of stuff. So the information that is used to create those bars are these framestats that we have underneath. We have this sort of illegible data that you can get by running this host command. It gives you the timestamps of all of those pieces of information, input handling, animation, the stuff that we saw, the draw. So we tell you exactly when that thing happened, and you can take this data and you can copy it into a spreadsheet if you'd like, or you can use something else to aggregate that instead. gfxinfo gives you the same information, but it's aggregated into these nice histogram buckets. It tells you how many frame events were in the duration of all of these different buckets, and then what the percentiles were. So how many of your frames, it turns out that 90th percentile was at 48 milliseconds. So like does that mean 10% of the frames are actually popping way above, like they're missing 2 frames? Probably not a good thing, right? So the way frame metrics...
Those dumpsys commands that we just showed for the histogram and the frame stats, you can run them in automation. So that's what we use internally at Google. We create dashboards. For every build that we build on our build servers, we run that data on specific scenarios for several of our apps. For instance, we launch Gmail, we scroll the app, and then we gather the frame data, then we have a beautiful dashboard. And it's extremely useful because every time we have a new build that brings the performance down, we know immediately. So this is something I highly recommend you do, like automate that. Like performance, it's really hard to do after the fact. If you wait 6 months to do your profiling and then you're like, oh, things are slower than they were 6 months ago. Well, good luck finding the reason for that. If you do that on every build, and for us a build can be from 1 to about a few dozen PRs, you're going to be able to quickly identify the root cause of the issue and at least revert it until you have a solution. So yeah, use those in your continuous integration if you can.
So I have some information here about how to use the FrameMetrics API, but I have a better idea, which I'll get to given the time that we have. So you can add a listener, you get information on every frame, you do something with it, you aggregate it yourself, you upload it offline and analyze it. But better yet, there's a new API in SupportLib, the version that came out around the I/O timeframe. It's no opt prior to end because the platform functionality wasn't there, but you can use it in your app to get information in a much better way. You can basically get that same histogram data that we saw in gfxinfo directly in your app. So you create a FrameMetricsAggregator, you add whatever activities you want to it, and then whenever you want, you get the metrics. And the metrics is basically that array of information for the various durations that you asked for with the flags when you created it. And then you do whatever you want with it. Also, I should point out that we aggregate this data already and we upload it to the Play Store dashboard. That started around the I/O timeframe as well. There was a talk by the Play Store team where they talked about this and other information. So you can actually see aggregated jank stats for your application, which is great. And then you can see, well, oh, when we came out with this release, our jank stats got worse. But if you aggregate the data on your own, if you track it at least on your own internal dashboards using the approach Romain talked about or the APIs we're talking about, then you can get a much more fine-grained view of what's going on and why. And with that, I will end with a French word. There were 2 performance talks that were at I/O. If you haven't seen them yet, they're probably worth checking out, especially if you want to know more about systrace. Tim Murray gave one that was a real deep dive into using systrace, lots of tips and tricks about that. That was the overview. And then Chris Craik and I gave an overview of various performance tools and APIs and use cases. So you might want to check out that one as well. And that is our talk. Thanks for coming.
Thanks.